Hi guys, this is Jeff Coronado at JCSC, and this is an ongoing sequence that we entitle Bridging the Gap, where we basically try to help young structural engineers bridge that gap between what they've learned at school and kind of what they need to know as they start their career in practice. So let's see, the title of this tutorial is How is the Footing how's the footing for a manufactured building designed? Okay. Again, it's an ongoing sequence of tutorials that we produce here. Some of them are in-house. Some of them we do allow you on the outside to view. And again, it's just intended to help you with an understanding of structures. So this was a question that actually came up on a project, which is how is the exterior continuous footing for pre-manufactured metal building designed? That was kind of the crux of the question. So it's a project where we are designing the foundation for a pre-manufactured building. So, okay, so for reference, the detail is MBF1. So, so if there's any questions in this tutorial about any of the values or data, it could be that there's other aspects of the design were covered in other tutorials associated with MBF1. So you can look in our channel for the tutorials that include the name MBF1, and you might find the information there. Hint, so get all you can from the tutorials. I know that sometimes people have the habit of kind of like jumping around, listening to one part, listening to another, getting a value. And I've got to caution you, in the long run, you're shortchanging yourself, you're shortchanging your development. I think it's like a lot of things. If you go back to school and think about when you were in school, the more you're able to digest the lesson, understand it, then the better off, the better equipped you're going to be to handle not just that situation, but any other situations that arise that are going to be similar in nature. And that's really what we're trying to do here, is kind of get you to start thinking like a structural engineer. So the sooner you can digest this material, not just the explicit value, the explicit number that we're discussing here, but the thinking process, then the sooner your career is going to take off. So that's just kind of a hint. If we scroll down here a little bit, so this is, you can see in the lower right-hand corner, that's the section that we're going to be dealing with. So that's a cross-section of the slab on grade and the perimeter footing. What you see there is steel reinforcement. Let's see here. So we've got steel reinforcement. This here, this is our negative reinforcement. Okay, so we've got a bar that you can see going across here, and then you've got bars going into the page here, right? This is our negative reinforcement. The purpose of the negative reinforcement is covered in another tutorial in the Bridging the Gap series, so I'm not going to get into that here. Top and bottom reinforcement in both directions. Okay, down here, you can see the bottom reinforcement, and then the bar here going from left to right, which is right here. And then you see the bars that are going into the page, in and out of the page, which is what we would call the continuous reinforcement. You can see that above there. So let me clear that, and let me scroll down here. Okay, so we have a continuous footing along the perimeter. Let me stop here and see if we can sketch this out a little bit. Okay, so getting back to a hypothetical type structure, I've done a simple diagram here. Really, the complexity of the structure doesn't alter the lesson here, if you will. What we need to learn applies to whether this is a rectangular, a simple rectangular footprint like we're showing here, or whether there's re-entrant corners or what have you. So let's say the perimeter of the structure is in black, and let's say that the blue represents columns, okay? So those are columns. They can be wide flange columns, and in all likelihood, they will be wide flange columns. So we've got wide flange columns there. And let's say that hypothetically, these columns are spaced at 20 feet apart, okay? So each one of these, right? So this one, let me use another color. So this column and this column, right, that's 20 feet. This one's 20 feet. Let's just say the columns are at 20 feet apart. Okay, we're focusing on the downward force acting on the perimeter. So these columns can bring a multitude of forces. That's not what we want to cover in this tutorial. That's covered in other tutorials in the bridging the gap sequences or sequence. But in this case, we're going to focus initially on the downward force that we have on these columns. So let's say that hypothetically we've got a downward acting force of 10 kips from one of these columns. Okay, so we're going to have, you know, undo that. Let me try that again. Okay. What is wrong with our arrow here, guys? One last turn. Yay. So there's our force acting downward on our footing, right? So let's just say hypothetically we've got a 10 kip load from one of the columns, or from each of the columns, pushing downward on the perimeter footing. So, you know, typically when we have a column, or typically, you know, more often than not, when we have a column, we have what we call a pad footing. Designing a pad footing is not the purpose of this tutorial. That's covered in another tutorial. If you have any questions, by the way, on any of our tutorials, by all means, send me an email and we'll try to answer them. If we need to try to point you to other tutorials that we have, whether it's on our public channel or not, we'll see what we can do. Okay. So we've got this force acting downwards on this concentrated force acting downwards on a perimeter continuous footing. So we have one dimension for the footing is obvious, right? If we go back to this sketch, sure enough, one dimension is obvious. Let's see if I can label it. So the width of the footing that's going to support that column is obvious. That one, let's just call this dimension B. Okay, so getting back to the other dimension, what dimension do we take on what dimension do we take in the other direction, right? The one dimension B, that's obvious. But how much of this continuous footing is it reasonable to take to resist the force that's imposed upon it by one of these columns? So, okay, just as a possibility, I'm throwing out a suggestion, I guess, an option. Change this to use another color. How about magenta? All right. So, so I think one possibility is this red dimension. Oh, by the way, I don't know, have we talked about this yet? So in blue are the columns, right? So we're kind of looking at an overall elevation where we've got a column here, column here, column here. Okay, so the columns are in blue. Our footing, our continuous footing, is shown here in black, and then here's the soil below the footing in brown. Okay, so get rid of this. Am I able to get rid of this? Ah. Oh well, I guess I don't need my soil. I'm not going to battle that one for now. You get the point, right? So there was soil underneath the footing. So the question is, what's the effective dimension that we can take in the other direction for this continuous footing? So yes, one possibility would be this dimension right here. Let's say this is B. Let's say we match the same dimension as we had in the other direction. Would be one possibility. Another possibility is this green dimension that we're showing here, literally a center to center distance. Okay, so let's just say this and this and this, so that these are equal. Okay, so let's say equal and equal here. All right. So in essence, we split the distance between the columns and we say that's the effective dimension of the footing that we can use. All right, so think about it for a second. How much of this continuous footing can we use to resist the load? Again, can we use this amount of the footing? Can we use this amount of the footing? How much of the footing can we use to resist the load? Well, here's how we would do it at JCSC. The magic number that we would look at is 4 times the thickness. And that's 4 times the thickness on each side of the column, okay? So 4 times the thickness, I'm sorry, 4 times the width, I should say. Sorry, now I'm getting confused. 4 times the thickness, right? I said it correctly initially. Four times the thickness, so not the width that we've been looking at, but 4 times the thickness of the footing. 4 times the thickness of the footing on each side of the column is what would be a reasonable amount of footing to take. That's how we would do it at JCSC. So we would take 4 times the thickness of the column on both sides and figure that's in essence your pad footing to resist the pressure from that column. Anything more than 4 times the thickness, use yellow, anything more than 4 times the thickness, if we start to venture out and say, well, you know, what about using this amount of the footing to resist the pressure from the column? It's doable. It's not that it would be wrong. It's doable, but it would require more thought. Okay, and so that's a matter for another tutorial. So if you wanted to do that, check back in with me. I don't know if we have a tutorial for that or not, but check back in with me and we can discuss it then. But as long as you're not venturing beyond 4 times the thickness, we can treat it conventionally. You can design that positive reinforcement, that bottom steel, for a pad footing that has a footprint of B in one dimension and then literally 8T in the other dimension. If you really wanted to push it, you can also look at the width of the footing. I'm sorry, the width of the column. So you can take into account the width of the column. So by that, you can see this sketch up here, okay? So this little portion of the sketch. So we've got a footing, which is in black, the column in blue, right? The column is going to have a base plate. That base plate has a finite dimension. It's going to be whatever, 10, 12, 24 inches. It's going to have a finite dimension. So you can take the effective length of the footing to be 4 times the thickness projecting out from the edge of the base plate. However, keep in mind that that is pushing it, right? That is pushing it. Your best bet is to not take it from the edge of the base plate and just take 4 times the thickness from the center line of the column. So you go 4 times the thickness from the center line of the column in both directions, for obviously as long as the footing is there. Okay, so let's just say the footing only goes to 1 or 2 times the thickness of the footing on one side, then that's all you can take, right? Is that 1 or 2, whatever this distance is. All right, but provided you have, what you don't want to do is take more than 4 times the thickness of the footing going out in each direction. So, but let's say for this situation where you have a column in the center of the footing, and this one where you have a column in the center of the footing, then you're able to take 8 times the thickness of the footing as the dimension, as the other dimension for the footing, and then assume it to be just a pad footing with those 2 dimensions, b in one dimension in one direction, and let's say 8 times t in the other direction. That's your pad footing. That's how you would design your steel reinforcement in that area. I'm sorry, that's how you would design the steel reinforcement to resist that column. Then what we do is just extend that reinforcement throughout the footing. So even when we're not underneath the column, we just typically use the same reinforcement that we've designed for the area under the column throughout the perimeter footing. Okay, that's how we go about obtaining the positive steel for a continuous footing. Let me go back to the question here just to make sure we covered it. Where is it? How's the exterior continuous footing? Yeah, we've covered the steel reinforcement for the continuous footing. Again, the negative reinforcement is part of another tutorial in bridging the gap. But we've covered the positive steel. All right, so if you found this to be useful, I'd appreciate it if you give us a thumbs up, just to know that it was useful to you. If you have any comments or suggestions on how this could better help you, by all means, feel free to leave me a comment in the tutorial. We'll see what we can do. If you have any questions, feel free to leave me a comment in the tutorial, and we'll see what we can do. Okay.